Okay, well, thank you, Danny, for the nice introduction. Thank you to everyone who's here in person and to all of us joining online today. My name is Phil. I'm a postdoc here at Macquarie with Danny Turner's group. And today I want to tell you about the Euclidean path integral, some of the nice features that it has and how we can apply it to learn things about black hole physics. I will mention some of the recent work that I did with Ioannis, which he talked about earlier today. And at the time that we did that work, we weren't really thinking about quantum information too much. So what I kind of want to do is introduce some information theoretic features to do with the Euclidean path integral and then try to reinterpret some of the results that we got in that paper in light of these types of things. So the outline of the talk is as follows. I'll mention black hole thermodynamics in general, which is the central thing that we're studying here. I'll talk about path integrals, what they are, what we can compute with them, and then discuss some various applications therein. As we know today, there's a very good reason to believe that black holes are relevant experimentally and observationally, and this will prove to be true even more so in the coming decades as observational technologies reach unprecedented levels. But for much longer, black holes have served as an important theoretical testbed to test information theory and quantum gravity. And this is because black holes seem to, despite being classical vacuum solutions to general relativity, possess thermodynamic properties. So if you believe, now Danny mentioned many alternatives to this, but if you believe that gravity should be quantized, then presumably, like other thermodynamic systems in the world, the thermodynamic description arises from some coarse graining of some microscopic degrees of freedom, which is exactly what you're trying to understand in the context of gravity. So the usual story is that variations between the mass or energy of a classical stationary black hole solution are given by a variation which looks much like the first law of thermodynamics, with kappa being the Hawking temperature and this area playing the role of the entropy. So this is one of the biggest hints, actually, that there's something strange about gravity compared to ordinary systems, and that's the entropy scales like the area and not like the volume of the system. If we want to assign a state counting interpretation to this entropy, usually this is given as a sum of the microstates that you have associated to some macroscopic quantities that define the state, and this usually scales like the volume of the system, but for a black hole, it's scaling like the area, and this tells us something about the holographic nature of gravity. In the modern covariant formulation of the first law arises from considering a flow in your phase space associated with some diffeomorphism generating vector field xi. This is in general this variation given by an integral of the symplectic current over some Cauchy surface. But now if you have a black hole background and this is a diffeomorphism generator, then this quantity evaluates to some boundary integrals at the horizon and some integrals at infinity. And these quantities are variations of the ADM mass, the angular momentum, and so on. And the quantity on the left, which is the integral of this conserved Noether charge 2 form, gives you the heat term TdS. And this S is the walled entropy. So in Einstein gravity, this is proportional to the area of the horizon, but in general, it's just the integral of this Noether charge 2 form over the horizon. And I'll come back to that walled entropy when I talk about entanglement entropy, so that's why I mentioned it here. Now let me talk a little bit about the path integral. The path integral is very nice because it provides, let's say, an alternative way to define quantum theory. Quantum theory is defined by transition amplitudes and correlation functions, and the path integral computes a transition amplitude between some initial state and some final state given by the action of a unitary time evolution operator. And formally what you do is take the action of this unitary and observe that it satisfies this very nice convolution property, which allows you to break down the evolution from the initial state to the final state into a bunch of infinitesimal sequences of steps, with epsilon being the small time difference between the initial and the final state for very large n. So you have a very large sequence of these steps given by the action of successive time evolution operators, U, and what emerges is this picture of summing over all of the intermediate states that take you from the initial state to the final state, which gives you the amplitude to go from that initial to final state in the end. At each step, you insert a complete set of momentum eigenstates that you sum over, and so in the end, you get this measure for the momentum and the position eigenstates, and the Lagrangian there emerges from doing a Gaussian integration, and you have the discrete form of the path integral. And I should point out that formally the path integral is only well defined strictly when you're at this discretized level. As soon as you go to the continuum, which is the usual way that we use it, this is formally ill-defined, but nonetheless extremely useful for computing all kinds of different interesting quantities. This is what we'll use. It defines a quantum theory in the sense that it serves as a generating functional for all of the correlation functions in the theory. So you insert some fictitious current J, you take functional derivatives with respect to J, and this gives you whatever correlation functions you're interested in. This is true for a general quantum system. Another thing you can compute is the partition function, which is what I'll be working with today. And this is given by a trace of this Boltzmann factor. This Boltzmann factor is just the time evolution operator where the time interval is imaginary. So beta is minus IT. And computing the trace can be done by just summing over all paths where the initial state and the final state are equivalent and periodically identified, where the periodicity in this imaginary time is just the inverse temperature beta. So we compute the partition function for the quantum system by doing this path integral, where this exponential is now e to the minus classical action of the theory with no I. So the point is that this seems to give you very reasonable results when you apply it not to some quantum field phi, but actually the metric g. And it formally defines a quantum theory of gravity in this sense. Now, this gravitational functional measure is ill-defined in the general case. So usually what you work in is a semi-classical approximation where you argue that the dominant contribution to this path integral comes from stationary points of the action, which are the classical solutions to the equations of motion for this action E. And you just sum over all of the classical solutions which satisfy the given boundary conditions for the problem at hand. Once you have the partition function, you can compute the mean thermal energy of the statistical ensemble that it defines, the entropy, which is what I'll focus on today, the free energy, and so on. And you can see that these quantities, you can't see, but you can show that these quantities satisfy a first law of thermodynamics for the case of black holes, equivalent to the Hamiltonian formulation where both apply. S here is that walled entropy, which I mentioned before, which is not always equal to the horizon area of a black hole. So let me talk a little bit more about entropy, because the biggest open problem, I guess, in black hole physics, one of them, is what is the nature of the entropy? What is it actually counting? What are these microscopic states? And one conjecture is that it's somehow related to entanglement entropy. So entanglement entropy arises from, you have some system, and you consider a boundary that separates two different subsystems. You partition out the one subsystem, compute the reduced density matrix, and you have entanglement, which results from ignoring the degrees of freedom on the other side of the boundary. Now, when you compute the entanglement entropy in the general case for a black hole or any other surface, it's given by the area of the surface divided by epsilon squared, where epsilon is some UV cutoff. And this is because when you compute this, you're summing over an infinite number of modes with higher and higher energy, and so this will diverge. So this looks very different than the black hole entropy, which is just A over 4 and does not diverge. And so the question is, can we understand how these are related? There's a nice result by Susskind and Blum from 1994, which shows that the entanglement entropy, when you consider the horizon of a black hole as being the boundary that partitions your two subregions, the UV divergence here is actually regulated by renormalizing Newton's constant. Okay, so what you need to do is include not the Einstein-Hilbert action, but you also need to include one loop corrections to the Einstein-Hilbert action, These come in the form of curvature squared terms with some coefficients, and then regularizing the divergences that appear in those renormalizes the value of G, but it does so in such a way that the entanglement entropy is finite and is equal to A over 4G. But now this G is not the bare Newton's constant, it's this renormalized Newton's constant. Okay? So indeed, in this sense, the entanglement entropy can be seen as at least contributing to the black hole entropy and being finite. I'll come back to that. How do you actually compute the entanglement entropy? This is very difficult because you have to remember the trace.
So this is one result of this normalization.
This?
Oh, yeah.
Yes. So to actually compute the entanglement entropy is very difficult in the general case because this trace was given by a path integral, and you're taking the logarithm of some infinite dimensional matrix in the general case, and it's very hard to do. So there's an idea by Callan and Wilczek, and indeed Susskind in that paper did a similar thing, where you consider the entropy, and we're instructed here to vary with respect to beta when computing the entropy, which is the entanglement entropy. Now, in the Euclidean version of the geometry, the black hole geometry, in the general case, you have a cone with a singularity where the horizon is. Okay, and this singularity is only not present if a particular choice is made for the periodicity in imaginary time. Okay, if this is not equal to 2 pi, then you have the metric of a cone, and you have some singular geometry. In flat space, there's no horizon, and you can choose any periodicity for tau. Your metric is just R3 cross S1, and regardless of the radius of this thermal time circle, you have no conical singularity at all, and everything is fine. So things are quite subtle in the black hole case. Choosing beta to be equal to 2 pi, so that you have no conical singularity, is equivalent to just restricting yourself to the smooth Lorentzian geometry. What Callan and Wilczek did, it's called this replica trick, is to consider variations away from that smooth choice of beta, parameterized by delta. So delta is this deficit angle, which when it's 0, you have the smooth geometry. When it's non-zero, you have a cone. And they showed that this entanglement entropy that I showed before can be computed simply by considering this deficit angle, acting on the partition function, and taking the limit as this deficit angle goes to 0. And this is this replica trick, which is used commonly today in computing entanglement entropy. To prove this formula, they use the replica trick, but I don't have time to get into how exactly that works. So we'll just take it to be true for now. And just 1 year later, it was shown that this entropy is actually the same as the walled entropy when it's properly renormalized. Okay, so when you compute this quantity, the entanglement entropy, you're computing the walled entropy. There are some conditions here, some restrictions. Some of these have been lifted in the intervening years, but originally you required a bifurcated killing horizon for the entangling surface, and this would not work unless the Lagrangian is only linear in the Ricci scalar. If you had higher order terms, then these two entropies would not be equivalent anymore. Okay, so I will come back to the entanglement entropy when we talk about our regular black hole example. Now I want to talk about another nice feature of the Euclidean path integral, which is that it allows you to compute thermodynamics for black holes in asymptotically de Sitter spacetimes. So in asymptotically flat space, or de Sitter, a black hole will eventually just evaporate, so it's not at equilibrium, and so you can't really talk about equilibrium thermodynamics. Things are even more difficult in de Sitter because you have a cosmological horizon, and the temperature of that cosmological horizon is different than the black hole temperature, so there's a heat flux between the two horizons, and you don't have an equilibrium ensemble. So the idea is to put your black hole in a cavity, and you fix the temperature at the surface of the cavity, and this furnishes an equilibrium statistical ensemble. And this is accomplished exactly by taking the Euclidean path integral, which computes a partition function, but now instead of integrating over the entire manifold, which would formally diverge in asymptotically flat space or anti-de Sitter, you have some subtraction term there to regularize that. But now you just take a finite boundary, which is the cavity, and you only integrate over the interior of that boundary, and you fix the temperature at the boundary, and this gives you the partition function at that fixed temperature, whatever temperature you specify at the boundary, and then you can compute the entropy, the energy, anything else that you want with a well-defined temperature. So in the example that Ioannis mentioned earlier today, we considered this class of regular black hole solutions, which serve as a nice classical model of a regularized geometry arising from some quantum theory of gravity. As he mentioned, they're sourced by magnetic charge, so they're not physical, but they illustrate some of the nice features that we expect to arise from a regularized classical black hole geometry that we can study. And we studied this using this Euclidean path integral in asymptotically flat space, asymptotically anti-de Sitter and de Sitter space. And one of the nice things that we showed, there is no form of the laws of thermodynamics for black holes that applies for every single type of black hole solution with every single type of asymptotic structure. You need to pick and choose which formulation you apply in which case. And especially for theories of nonlinear electrodynamics, the form of the first law is only known when you know that the gauge field inherits the symmetries of the underlying spacetime. So if you have a spherically symmetric background and a spherically symmetric gauge field, then there's a known form of the first law which holds. But in our case, we don't have that because we don't have the symmetry inheritance for the Hayward model. And so one of the nice things that we showed is that even in that case, in the absence of a proof of the form of the first law, it actually does satisfy the usual form that you expect. And furthermore, the smart relation there is linear. This, again, ordinarily relies on having this electromagnetic duality relation to prove linearity of the smart formula, and we have that here as well. As mentioned, we have...
Duality relation holds for the nonlinear case?
It does for the Hayward one, I think. Yeah, it does in that one. But we don't have symmetry inheritance. So
regarding the symmetry on the field as of the symmetry of the spacetime, so is that like people usually do? Or?
People usually do, and it seems like a natural assumption, but you can come up with, even in Maxwell electrodynamics, classical solutions which do not have this property, which are nonetheless still solutions to the equations of motion. So there are known counterexamples even in that case, but most of the time you do have that. So let me not talk too much about these phase transitions, since Ioannis already mentioned that we have these variety of small to large phase transitions that ordinarily can be mapped to fluid-like transitions and have some important interpretations in holography in terms of ADS CFT. One of the notable things is that when you're in asymptotically de Sitter space, the bulk phase structure is very different than it is in asymptotically ADS. In ADS, here with negative cosmological constant, you have one second-order critical point terminating the swallowtail, and then a sequence of first-order phase transitions between a small and a large black hole occurring above some critical pressure. But in de Sitter, you have two second-order critical points which bound the region in your parameter space where you have the first-order phase transition. And so you get significantly more complicated phase diagrams, which we expect to have a lot of interesting applications in de Sitter CFT holography. So the question that I want to come back to, this is all interesting in its own right, but we computed the entropy here from the Euclidean path integral, and the question is, what entropy did we get? Because I talked about a few different ones. And the entropy we get is pi r squared. So is this the walled entropy? Is this the entanglement entropy? Well, remember that the walled entropy is always the entanglement entropy, but whether or not it only includes the classical geometric contribution to the entropy or quantum contributions from entanglement which renormalize G, this depends on what action you used. So if you included in the path integral all of those conical singular geometries, then what you obtain is the renormalized walled entropy, which contains the quantum contribution from entanglement and also the geometric contribution. In this computation, we only used the geometry with beta is equal to 2 pi, the smooth geometry at the horizon. We did not include those conical geometries, so this must be the ordinary walled entropy with the bare G. And to compute the entanglement entropy, you would have to add those higher curvature terms to the Lagrangian. So that is something that is worth doing and that we're going to work on next, is how to extract the entanglement entropy by working at the one loop effective action instead of just the tree level gravitational action to see what happens. And just to mention that the Euclidean path integral can be used in a variety of different settings to calculate interesting thermodynamic quantities for all kinds of different classes of theories and all kinds of different asymptotics for your spacetime. And there's lots of interesting bulk phenomena that you can observe there. So with that, I'll end, and thank you.
Right, now it's time to ask some basic questions.
Yes.
Not a question, yeah, very nice talk. I just wanted to mention that Giat Valley collaborators were looking for the quantum field theory systems without gravity, which has a similar separation of the entropy, like black holes. So maybe it will be for you interesting to look from the path integral perspective of those QFTs. Some of them are actually exactly solvable models, like a Grosny-Mu model in larger.
And they're computing entanglement entropy there?
Yeah, well, I mean, they can show that in a certain limits where they exactly can compute this entropy related to the unitarity bounds in that particular case. And so those systems, as a bound state system, behave exactly the similar way as the black hole. So it's like an analogy. You may want to try all this field theoretic methods where you can use your path.
No, that sounds very interesting. I mean, the path is.
My postdoc who is now with me will be in ANU. Maybe you can talk to him.
Okay, nice. Yeah. I'm always looking for new applications, and a lot of stuff is done in just 2 dimensions. Because there you can work Gaussian, but yeah, definitely very interesting. I'll end here.